It could be quite difficult visualising the shape of complicated geological boundaries like irregular unconformities. So in this short video, we'll look at how we can construct structure contours on an irregular unconformity surface. We'll use an example from Western England in the Mendips area. We'll set the scene with a sort of regionalish map for the area, and then we'll look in more detail at a small part of this map area using the topographic information on this simplified geological map. To set the scene, let's use this map for the Cheddar area. The area we're going to look in detail is this one in here. And you can see that this is part of a fold structure that's closing to the right. It's got older rocks in the core, so it's an anticline. The dips are outwards away from the core of it, so it's also an antiform, plunging down this way, so we have a fold structure. But overlying the fold, apparently taking bites out of it, are these yellow rocks which are Triassic. They include a unit called the Mercia mudstone. And we can see they've got these rather strange geometries. So what we want to try and understand are what are these geometries which look like sort of teeth in this sort of area here, which we can use as a test bed. So let's look at the more detailed map and crack on with that. What we can see on here are the topographic contours. Always useful to get your eye into the topography. And they're these little valleys in the topography picked out by the contours cutting back in again. And it's really interesting, isn't it, that the Mercia mudstone, these Triassic rocks, are actually sitting in the modern valleys. So where you get these embayments in the outcrop pattern, they coincide pretty much where the topography cuts in. So that's a concept we're going to explore, and we'll do it by trying to draw some cross sections first of all to get an idea of the structure, and we'll start off with A, B. Right, so let's get a map strip, a pencil, and we'll collect the information along the section line first of all. So let's zoom us in. Okay, so I'm just going to measure up from B, so let's put mark B on here. And that's where the edge of the Mercia mudstone is, and then we've got this limestone unit here. Whoops, just straighten that up a bit. Just there, this other one there and there. So let's transfer that information. Sorry, let's just tighten that up. That's the start of the section line B. Let's take that information and put it onto the profile. So let's plonk that onto B, just there. And I can see that the edge of the Mercia mudstone is there, so I'll just put a tract of yellow along the edge of the outcrop there to signify that's the Mercia mudstone. And then coming along to there, it's where that boundary is there, and that one is there. So those are our rocks. Let's just put some patches of limestone colour on here, a bit of blue, and then all this is the blue unit coming through like that. Okay, just so we know what we've got. So the question is, what happens at depth? Well, for that we're going to draw some structure contours. So let's quickly sketch some contours on the base of this limestone here, which is the Clifton Down limestone. So I can draw a structure contour where that 150 topo intersects the boundary here and there. So there's a structure contour running like that. And we can do another one on the base of this limestone unit representing the 100-metre contour, and that runs through there like that. So we've got two structure contours on the base of this limestone. So let's collect that information and put it on our profile. So we line our map strip up back with the profile like this. There's one structure contour, there's the other structure contour. That's the 100, that's the 150. So we can take that and put it onto our profile, put that here, line it up, I'll get it right up onto here. So there's B, let's put the 100 contour on, so line up with the 100 elevation on our profile, and that's the 100 pick just there, and the 150, move up to here for the 150 pick, it's that line there, and it's just here, just behind the outcrop point. So we've got two places plus the outcrop on the boundary, join them up, and there goes our boundary to depth of the base of the Clifton limestone. And I'll just colour it in so you can see it go through. So a simple bit of cross section through there for the base of the Clifton limestone. Next then, what about the Cheddar limestone, which is this one here? And I'm just going to sketch some structure contours on that. I'll just use this green pencil for that. And here's the 150 intersecting the base of the Cheddar limestone, there and there. Join those up and they come through like that. Notice they're parallel to the structure contours that we've already drawn on the Clifton Down limestone. But there's only that one that we can put on. Let's quickly capture that one. There's the line up. There it is on our map strip, clunk, and that's, just remember that's 150. So I'll take that to here, put it onto our profile, B, it's 150, so line it up to the 150 elevation, put the B in the right place, and it's just there. So that's a point on the base of the Cheddar limestone, and that comes to outcrop here, so we can sketch those 2 points in. I'll just project it on the same trend like that, and I'll take the top as well while I'm at it. So there, this little thin limestone, the Cheddar limestone, going down, and again I'll just colour that in with limestone blue. So we got dipping limestones inclined down here towards B, towards the south. So what have we learnt then about the rocks that underlie the Mercia mudstone? Well, they dip south, therefore they strike east-west, and we can just confirm that by looking over here, and we can draw some other structure contours that would sort of come through here. There's the 150, so that would come through somewhere like that on the base of the Clifton Down limestone over in this part of the map. We can do the same over here. There's another structure contour we could draw here that comes through. So the strike is coming like this. What we're going to do now is draw a profile along the strike direction for these older strata. Now, this is running along the strike, so it means that the profile will intersect the units of these older strata on strike, and therefore they should plot more or less horizontally. So I'm going to really be interested in how the Mercia mudstone cuts in and out of this line of section. So let's get a map strip and start plotting the intersection along the section line of where the Mercia mudstone comes to outcrop. Okay, so here we go. Let's line it all up. Pop that along here, and we'll just put X on here. So it intersects there, 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 and just there. So there are 1, 2, 3, 4, 5, 6 pieces of Mercia mudstone that we see on the section line. So let's take this information and plot it on the profile. There we go, line it all up. Like that, so let's line this up more or less at sea level for the sake of argument. Whoops. And let's just do it. Here we go. 1, 2, 3, 4, 5. Let's just get that lined up a bit better. There, 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 there. And just bring that up a bit so that it gets, because that's slightly higher ground. Line it up a bit more carefully. Let's bring it right up. So here, and there it goes, there and there. So that's the information that we've got, and let's just put that some colour on that, and we'll just check as we go. So this little piece here is that tract of Mercia mudstone. We've got that piece there, which is just in here. We've got this very broad piece, which is in here. We've got another piece as we cross section line AA primed, which is just there. I can't really see. Let's just check my pencil marks. It's this tract in here, and there's a little piece here, and then finally all this. So 1, 2, 3, 4, 5, 6, which are the 6 pieces that we saw on our profile. So now we need to join these up by creating a surface that continues in the air and in the subsurface. Well, the Mercian mudstone's on top, so therefore the Mercian mudstone outcrop must continue and have been eroded over the top of this ground. I'm exaggerating it a bit, perhaps not quite as high as that, and then come down to there and then cut out again and down and out again and down, out again and down, out again and out again, so that the Mercian mudstone lies in low ground. Now let's take the bit below surface like this, like this, like this. This one here, this little piece here is only just missing the outcrop, so that's only just under the ground there, and then goes out, and a little piece there, and down. So we have the unconformity at the base of the Mercian mudstone is roller coastering along, and it has to do that so that the Mercian mudstone lies on top of the other units in here that lie below the unconformity. So we have paleo valleys, old valleys at the time of the Trias, that have been filled in by the Mercian mudstone. So let's try and take this understanding from the profile and draw structure contours on this surface. Clearly, they're going to be irregular. They're not going to be straight lines like they were for the structure contours that we drew on the Clifton Down and Cheddar limestones earlier. They're going to mimic the valley shapes that we see in the modern world. So in other words, they're going to have loops on them that represent the valleys and ridges on the paleo valleys in this paleo topography. Okay, let's do this a bit carefully, and let's just zoom in to start with on this little area here to see the shapes and how they might work. So let's just pick this 100 metre structure contour. So here we have the topographic contour of 100 metres intersecting the boundary here and here. Now, there's some rules we need to think about. So the structure contour we're going to draw will only cross the geological boundary at 100 metres when there's a coincidence of the topographic contour with the geological boundary. So let's just draw this in. It's going to come through here. It must be in the subsurface so that the Trias sits on top. So it has to be down here and come back out again. And it can't cross this boundary here. It's got to come out, and it can't cross the topographic contour either. So it has to come around like this and like that. Let's keep going. And in this position, we can see 2 other points on the 100 metre topographic contour, and we can take that around like this and out, and then in and around like that, and so forth. How about over here? There is the 100 metre contour. So the structure contour is going to come around like that, go into the subsurface and back out again. So I have this general bow shape in and out, keeping it's constrained by the outcrop positions and by the positions of the adjacent structure of the adjacent topographic contours as well. Let's keep it going. So we've got our structure contour coming to here. In this position, the topographic contour is more or less on the boundary, so it actually is also the structure contour. And then it's going to emerge through here, around there. It must be constrained by the 100 metre topographic contour and the outcrop of the unconformity. So it's going to come round through here like that. It's heading for that point. So let's keep it going. It's going to go through like this, beneath the Trias, so that the value of the topography is somewhere between 100 and 150. The structure contour is 100, so it's in the subsurface, has a lower value. It's going to emerge back out there, so it has to swing all the way around here, tight around that, and back out, and really tight to the boundary in here, because there's the 100 metre topographic contour quite close by. Something like that. Could come a long way out around here. We don't quite know where it is in here, and then out. It's going to intersect there again, go into the subsurface. It's going to hit out here, so it's going to V around like this. Careful, careful. Around there, out and in, out, presumably something like that. It's going to head for here and on around the map. We can do the same for the 150 structure contour. A couple of picks here and here. I'll just do it in green so we can pick it out. It's going to come in, whoop around, stay on this side of the 150 topo contour like this, presumably. Let's just a little wiggle to honour that shape, and out somewhere like that and around. And as we come around here, it's going to have to intersect those 2 points and come out like that. So that's the structure contour, and we can keep going and going and going. So you can use the adjacent shapes to control, or at least infer, the geometry of the ones that are less well constrained, and collectively build up an array of structure contour patterns. It's pretty interpretive, isn't it? But it's surprisingly well constrained because of this rule about not being able to cross topographic contours or the boundary except at places where they coincide. We can just make sure this is all working, can't we, to honour the structure contour patterns and the section. We can take this longitudinal section where we suggested that the unconformity here was at elevation just over 150 metres on section AA, so we can take that information and say the unconformity is there. So here goes our unconformity, somewhere like that. These rocks, let's just keep them going down something like this in the subsurface, but the unconformity is eroding them away. Let's just add some colour to that, and we can see that the Mercia mudstone lies unconformable upon these inclined strata. So we can work between the two cross sections and the map to make a three-dimensional representation of this unconformity and its relationship to the underlying strata. So these strange embayments are paleovalleys. They are old landscape that the Triassic rocks were deposited upon. So the valley shapes in here we can see cutting into the substrate. And we've been able to understand their geometry in detail in here by drawing structure contours and profiles to get a 3D understanding of the paleo landscape that underlies the Triassic rocks.